So folks, in the previous example, we were asked to compute this triple integral right here. And we went ahead and did so by computing an iterated integral instead. And that's generally going to be our strategy going forward. But what's difficult about these triple integrals is even though we are still going to try to evaluate them iteratively, when we have convergence of the integrals, there are a total of 6 different possible iterated integrals. So we could integrate first with respect to x, then y, then z, or first with respect to x, then z, then y. And you can see there's a total of 6 of them. So I'll let you find the missing one, so you fill in. One of those is missing. And I'm going to show you how to set up one of them. Now, one of the things that we overlooked when we were working this problem up here, because it's almost too easy of a problem to really get a sense of what's going on, is how this iterative integral works for these more complicated situations. So the first thing I want to point out is here we've got our domain D, which is a surface in R3. So real quick, folks, just as a reminder, because we've said this a couple times, our function's graph lives in R4. We can't imagine that. Okay? So we can't imagine what type of hypervolume it is that we're computing. We don't have a real world interpretation of that in the world that we can see. Although we did see this example of where we can interpret that triple integral as computing a mass. That and all of those quantities are real and well known to us. So in this case, what I have here is our domain D, and our domain D has a certain structure. And in this case, it behaves sort of like a cylinder for part of it. So this part sort of looks like a cylinder. Those two slices, those two cross-sectional slices are identical, and where it starts to deviate is along this cap here and along this cap here that are on the top and the bottom. And so let's suppose that that cap up above is described by some function h of xy. And the cap below, we're told, is described by some function g of xy. Okay? So careful, folks, real important here. Our domain D is this solid. So it's very hard for us to imagine the difference between a surface, which would just be like standing on the outside of this shape, versus the solid. It's hard to draw the difference between the two. But we're talking about this as being solid throughout. That's really important. And in this case, the solid is bounded above by this surface and bounded below by this surface, and we're taking everything in between it. Okay? So that's our region that we're working with. So we want to go ahead and construct a triple integral for this, and so our goal is to evaluate this integral right here. We want to integrate this triple integral D of our function f of x, y, z, which is sort of the four-dimensional equivalent of volume is what we'd be computing. But if you like, you could imagine this as a density function, and so we'd be computing the mass of this solid object. Okay. Well, if we want to integrate this iteratively, one way we'll see this is since, the top and bottom, the g values, those are given to us, the z values are given to us in terms of functions of x and y, we're going to integrate first with respect to z in this case. Okay? So our innermost integral is going to be the function from g of xy to h of xy of our function f of x, y, z, and we're going to do that with respect to z first. Okay? That'll be the innermost integral that we evaluate. And if we think of it that way, this is going to give us some function, and so we have two more integrals on the outside, and we can think of those two as being a double integral. So let me go ahead and write that. We can think of those as being a double integral over some region R and taking an area there. And so what we're saying here is, here's this region R living in the xy plane. You can see it in the image here. And we're going to integrate we're going to find the volume above this region here, where we can't get the volume as a single function until we've actually done this integration right here. Okay. Notice that by the time we're done with this, we would be left with just some new function in terms of x and y after we've evaluated that integral. Okay. I may have lost you on that. That's okay. We're going to look at that more closely in class. But then how do we evaluate these double integrated integrals? This is what I do expect you to know. These double integrals we can evaluate as two iterated integrals. And so we're going to have the next innermost, which will be something with respect to y of that original. So let me see here. We've got g of x, y, and h of x, y. And we've got f of x, y, z, dz. That's our innermost integral. And so we're going to integrate next with respect to y. And we'll have to put bounds there. And then we'll integrate last with respect to x. Okay. This is where your work as a student has to really come in. And it has to do with sketching arrows on your domain set. Okay. So, notice that in this problem, we're told that that x is simply going to be varying between these two values right here, or this is our region here, and we can think of this as being bounded above by some function where y is a function of x, and then bounded below by some function where y is a function of x, and the x values are going to range between a and b. So hopefully we feel okay with this, and if not, we'll talk about this more in class, but this is going to go from x equals a to x equals b. And that'll be our outermost integral. Now, what I want you to think of doing in these problems is this sort of three-step process of how we say, okay, we're going to integrate first with respect to z, but one way we could say that is we're going to go out to a particular x value and fix it. So let me do that in blue here to match the colors that we were given. I'm going to go out to a particular x value and then fix it. Then I'll ask the question, well, what are my y values going to range between once I've fixed that x value? And my y values are going to range between this end point here and this point here. Or if you like, you can look at it in the 2D picture, saying we're going to go out to, say, this particular x value, x naught, and then we're going to evaluate this function, and that'll give us the lower bound here, g of x naught, and h of x naught will give us the upper bound. So once we fix an x coordinate, we then allow y to vary under that fixed x coordinate. Then for each fixed y value, so maybe this is the y value y naught that we get, so for that y naught value, we've now got an ordered pair in this space right here, and it's right there, x naught comma y naught, and then we're going to plug that ordered pair into the this expression here, which is going to give us a lower bound for z. This would be the ordered pair right here, g of x naught, y naught. That gives us a lower bound for z, and then the z values will range between that, let me do that in green, will range between this lower bound right here and this upper bound right here. So that upper bound there is this point right here, which is the point h of x naught comma y naught. So we first fixed an x naught. We went out to a particular x naught, and I did that. That should be a blue. I don't know why that came out red. We went out to a particular x naught. Then we allow y's to vary within that, and then for each one of those y's, we allow z to vary within that. So we go out a particular x naught. Then we go out to a particular y naught, somewhere between this bound here and this bound here, and then we go up to a particular z value, and that's how we're computing this triple integral. So, long story short, folks, this is going to go from y equals, let's see here, let's do that in the same color. That's going to go from y equals g of x up to y equals h of x. Now, folks, I expect if you're sitting here watching this video, this was a pretty complicated explanation. We're going to get more practice with this during class. This is the part for you to hone in on. This is what makes triple integrals difficult. It's understanding this process of moving out to an x value, moving then to a particular y value, and then allowing to z to vary around those points, and then go out to a different y value, allow z to vary, do that for all the y values in between here and here, and then adjust x value. That's what we mean by these iterated integrals, and this is what's going to take a long time for us to really get a grasp of.